All right. Hi, everyone. Thanks for joining us today. My name is Stephanie Wright, and I'm a principal in Nelson Nygaard's Portland office.
And my name is Brian Blanc. I'm a data specialist, also at Nelson Nygaard's Portland office.
Hey everyone, my name is Esther Needham, associate also at Nelson Nygaard's Portland office, and I'm going to be helping to answer some of the questions at the end.
So today we're going to share with you a tool that we developed for TriMet here in Portland that makes it easier and quicker to visualize bus delay, analyze the problem, and lead to solutions. So this has been for us a really data-driven tool to help us further transit priority treatments in the region. So we'll run through a presentation showing the tool's functionality and then go through a demo and then leave the last 10 minutes for questions. So if you have questions as we go, please type them into the Q&A box at the bottom of your Zoom screen. So the challenge we face is that buses are typically the workhorse of most transit systems and carry at least half of daily ridership. This is true in the Portland metro region, where TriMet ridership, 60% is on buses. But as traffic congestion increases, buses and the people on those buses are getting slowed down. This adds inconvenience for the delayed passengers, but it also means added cost for the system. So when cycle times increase due to traffic, agencies must add resources to keep up with frequencies. Bus ridership declined sharply during stay-at-home orders, but is slowly going back up. And cities across the country remain committed to making the bus an attractive travel choice by creating networks of transit priority corridors. So we know we need to invest in infrastructure that reduces delay and increases reliability. But then the question becomes, where is the delay happening and where is it the worst? So how can we target our resources? How many passengers are being affected? So where can we help the most people? And then what time of day and in what direction is delay happening so that we can target the solution to the problem? These are the questions that transit agencies are grappling with.
And thank you, Stephanie, for your introduction. I'm going to explain a bit about the development of the bus delay analysis tool, or as we've abbreviated BDAT. And then I'm going to demo the tool and leave some time for questions. So transit agencies get a lot of data, and that data set is always growing. Two of the biggest data sources are AVL, which is automated vehicle location, so a GPS mounted on the bus, and then APCs, which are passenger detectors at the doorways. Both of these data sets, as you can imagine, create a lot of records, and they're often used at kind of a microscopic level, whereas we're going to talk about more of a macroscopic use. Typically, transit agencies are analyzing performance on the route level. This makes it hard to understand street segment level issues where a street is served by multiple routes. We developed a better way to analyze all of this data, both through processing the data down to a more manageable aggregate, as well as aggregating all this data to the street segment representation that we developed. Additionally, we developed a dashboard to visualize all this information and allow for the development of project scenarios. First, I want to talk a bit about defining delay. We just kind of threw out that concept on the previous slide, and obviously delay itself is somewhat subjective, but we decided to go with a definition that relies on the distribution of travel times on a street segment. So in this case, we looked at the difference between the 80th percentile travel time, so I think a relatively long travel time, and the 20th percentile travel time, so think a relatively short travel time. For every trip and stop pair within the system, we took the difference between those two quantities, and then we were able to calculate a delay. That delay was aggregated up to the segment level, and then from there you can aggregate to the system and routes and all sorts of other aggregations. To help visualize what delay means for passengers, this is an example of a travel time profile over the course of a route. So you can see the green line referenced with the bottom arrow is the 20th percentile, the top orangish line, the 80th percentile. These are relatively long and relatively short travel times experienced by the bus over the course of the route. And the difference between them is the delay. Delay on its own is interesting, but a lot of times we want to weight that delay by other quantities we care about in transit planning. Most obvious one is passenger ridership on a bus. So you'll see that metrics 2 and 4 here take into account the passengers riding in a bus. So multiplying what's the average load of the bus times the delay experienced. Additionally, we also want to be able to normalize for service level. An express bus may experience delay differently than a bus that's running all day, and we want to be able to account for the amount of service provided. Additionally, we wanted to look at a different conception of delay as someone who maybe isn't a transit rider and considers delay compared to how fast they could travel in a car on the same segment. And so we compared the auto travel time and the transit travel time. Next, I want to talk about what segments are. So here you see a conceptual diagram of several different bus routes using the same arterial. And you can see the black numbers and lines indicate where we've split that arterial into segments. We split it at 2 major points where routes converge and diverge, like you see here, as well as major intersections that we hypothesized to have an effect on delay. It's important to note that these segments incorporate multiple stop pairs, and one of the advantages of the segments is that they incorporate routes that may use different stop pairs in the same segment. So coalescing all of the information into a common geography. Also important to note that segments are finer grained in most cases than time point segments, but you can roll them up to a time point segment level. Time points being major stops to which a transit schedule is pegged. We'll also talk about in the dashboard groupings of segments, including corridors. So when you have multiple segments along a roadway that you want to study, maybe in the project context, you put together them into a corridor. Additionally, we can roll segments back up to routes. So if you want to look at a specific route in terms of the segments that it uses, we can do that too. So now we'll talk about BDAT. It was developed based on fall 2018 and 2019 APC and AVL data, processed to the stop pair level, and then aggregated to our segment representation. And it was all developed in a platform called Shiny, which is a way to develop relatively lightweight web applications from R. So I'm going to stop sharing my PowerPoint, and I'm going to move over to Chrome here to show the dashboard. Let me just refresh this. Okay, so here's the dashboard. There's a bunch of tabs that we developed for various purposes. We're only going to go through a couple, just in the interest of time. So the one I want to start with is the Analysis Segments tab. So this shows the entire TriMet system in terms of its segments. You'll see on the map all of these segments that we developed and how they break up across the network. The way they are symbolized is both in terms of color. So the color notates whatever you've chosen as the map evaluation metric here, in this case, passenger delay. And the thickness notates the amount of passenger load on the segment. So in this case, you can see that information duplicated in the tooltip as well, so that daily passenger load. The color, a bit more on the colors, they indicate percentiles of whatever the metric is. So the dark red is the worst, the top 10%, the blue being the best in terms of delay in the lowest 10%. Below the map, you'll see some roll-up metrics. So these indicate service delivery and the delay metrics, and as well as the percent being covered by whatever your selection is. So it's also important to note down here, there's a bunch of filters related to time of day, cardinal and inbound, outbound direction, and some other geographies of interest to the TriMet service area. Additionally, as I referenced, you can change the evaluation metric you're looking at. So you can look at segment delay or passenger delay per trip instead of just pure passenger delay. So we'll do that now as an example, and you can see how the colors change. So where each segment falls in the distribution of that metric. So for example, Barber Boulevard was in the dark red category, just on pure passenger delay, but when you account for service level, it ends up somewhere more in the middle of the distribution. So we're gonna go back to regular passenger delay for the remainder of the demo. The next thing I wanted to talk about was we also have this table, which is a tabular representation of the same information on the analysis segments tab. What this provides is just a little bit more detail and a searchable, sortable table. So as an example, I'm going to sort to the segment that has the highest passenger delay. So in this case, it's segment 918 on Southeast Milwaukee. And then I'm going to go to the segment profile where I can dive into a specific segment and talk a bit more about that specific one. So here we can just search for it by ID or the name. We can click execute again. And this view allows us to see the segment that we selected. So in this case, again, Southeast Milwaukee, as well as all of the segments that have passengers flowing through that segment. So you can see on the periphery, where are there passengers that also flow through the segment that we've selected in the relative core here on Southeast Milwaukee. This helps to make the case for how improvements on a segment that might be relatively far away from the place you're trying to affect still have effects, in this case on the periphery. There's a number of plots down here related to load, trips, by direction and route on the segment, as well as travel time, the various delay metrics considered as well. I'm now going to hop over to a grouping of segments, in this case, a route. So I'm going to sample Route 72, which is one of our highest ridership routes in the TriMet system. And so here I can see whatever metric I've chosen, so in this case, passenger delay, as well as the boardings and alightings along that route. Just want to note also that when you're looking at the route level, all of the visualization is relative to the route level. So here you're seeing the worst 10% of segments along this route. There's a number of interesting plots we can make at the route level. These are typically things we used to put together for COAs in a bunch of different Excel spreadsheets, and this tool really helped us to speed up that process. So we are able to see a lot more detail with a lot less upfront effort. So loading profiles, travel time, headways, as well as these really cool plots. So these are heat maps of speed over time, so time on the y-axis and space on the x-axis, So you can see where is the bus slowing down in space and in time of day. Additionally, we have reliability heat maps. So these allow you to see, where is a bus may have volatile travel times. So, in this case, I'm pretty sure this area is just pretty consistently one speed versus this area is seeing a lot of volatility. And so, that definitely helps figure out what the appropriate treatment is. I'm going to then hop over, based on looking at Route 72, to one of the major corridor that Route 72 serves is 82nd Avenue. So here I can hop over 82nd Avenue, and I can see again all metrics relative to what's going on at 82nd Avenue. So the worst delayed segments here. You can see some simplified loading profiles. We do at the segment level instead of the stop level because of the nature of collating all that data by segment. Loading, variability in speed, travel time, again, so this is similar to the plot that I showed you in the PowerPoint, and some delay metrics as well. So this is all great exploratory information, but one of the real value adds we made in developing this dashboard was being able to select a bunch of these segments into scenarios where you're able to see what is the aggregate effect of all of these segments. So I'm just going to zoom in on one example here of a stock scenario that's in here. So this is the 3 different bridges in the Portland area that during the analysis period, so 2018, 2019, eastbound transit priority lanes, so on the eastbound approach to these bridges, were implemented. And so we were able to then see how did this change. So we can go back to the analysis segments tab and change to 2018 to 2019 comparison, and we can zoom in on the change in whatever metric we're interested in. In this case, I'm just going to stick with passenger delay. So for example, we can see on the steel bridge here how delay decreased over the analysis period from 2018 to 2019. We're hoping in future years to be able to add more data to this and see how projects have affected things. We just got lucky in this case that TriMet and BDAT were implementing this over the analysis period. So we were able to see this in the dashboard data. Okay, so now I'm gonna hop over to answering questions. So I think Esther has been cataloging those in the Q&A.
Sure, thanks, Brian. So one question we had was, how were the segments created or clipped? Was it done manually?
Good question. So it was kind of a hybrid process. We had in GIS kind of like split at intersection tool ready to go to take the first stab at it. So we just split where the route geometries intersected, but that definitely didn't result in a completely clean geometry. And so there was definitely a lot of manual tweaking that had to be done throughout the network to get it all to sort out cleanly. And then of course to split as well at those intersections we just know from the local context to be of interest.
Another question was, how were the plots created? What package did you use?
So those were all created in R. In some cases, they're created on the fly. So, as the app will just create the plots. In some cases, they are developed offline and we're just sharing the images of those plots. They're all created with ggplot, which is an R visualization package.
And where did you get the auto travel time data?
So the auto travel time data we got from Google. So prior to the COVID-19 pandemic, we queried a bunch of typical travel times by hour and by segment end to end for the whole system. So that's how we were able to compare the two.
Great, thank you. So another question was, how long did it take to develop this tool?
So first we did a fairly quick and dirty version in about 2 months to help with some project programming for TriMet and Metro. And then over the past year or so, we've made a number of improvements, including adding the fall 2019 data. The original was just the fall 2018. That probably added to an aggregate total of, I don't know, maybe six months of work. It was kind of on and off.
So how is TriMet using the tool now with the comparison and before?
Before, as I said in the previous version, it helped to identify where were the places that they could implement a project and get the biggest bang for their buck in terms of passenger delay, so most people affected. And then since then, they've used it for a lot of, instead of having to go into a spreadsheet and do a route profile by hand, they can just go directly to this tool and be able to see route profiles generated on the fly. So that's really helpful. The change feature, as I demonstrated, helps to make the case for the projects that they're doing. And as I said, hopefully we get more data in here in the future so we can continue to demonstrate as projects get implemented.
Okay, and so just one more question. Where is the data stored? For example, Amazon Web Services S3 server.
Good question. So right now, all this data is just stored in binary files in Shiny. We're actually working on another dashboard for another agency where we've moved everything over to a SQL database that lives in AWS. Probably the next iteration we do on this dashboard, we'll move everything over to a database just because it's getting a little bit unwieldy. This all started from an Excel spreadsheet database, so it's come a long way.
Okay, thanks, Brian. So that's all the questions. Actually, sorry, one more popped out. Let's just answer that one. And then
Okay.
Just want to remind everyone that we posted a link in the chat. So take a look at that for more info. So one final question is, how much additional lift is it to add additional years of data to an existing dashboard?
That's a good question. It's a lot less of a lift. It depends on a couple of things. So in TriMet's case, we made some segment changes. So between the 2 years, and so that added a little bit of work to the whole process. If you just wanted to add it to all the existing segments as is, that would be relatively quick. But still, overall, it maybe took us a couple weeks versus on the order of months to set up the initial one, because a big amount of the work is just setting up this segment representation. We just went through that on another project. Okay.
All right, I think we've answered all the questions. So Esther posted in the chat a link to our materials library. And thank you so much for being with us today. Appreciate it.
Thanks all.